Hello everyone, I hope you are doing well. So in this video, we're going to discuss Geeks for Geeks, problem of the day, and today's problem is construct a full binary tree, and it is a medium level problem. So before starting the video, if after watching this video you feel that this video was helpful for you, or if you were able to derive any value from this video, then consider dropping a like on this video, and also don't forget to share your thoughts in the comment section. Any general thing you would like to share, or anything about the problem that you wanted to share, you can write it down in the comments, because your engagement with this particular video really helps the YouTube algorithm to understand that this video was actually helpful for you, and it will be able to recommend this video to more people like you who want to keep solving new problems. Right. So let us quickly start with the problem discussion. This problem I felt like was pretty interesting. Again, a second interesting problem back to back from Geeks for Geeks. So that's very good. And today I did not face any issue with the test cases as well. So that is also very good. So the problem statement says that we have been given pre-ordered traversals of a full binary tree. Like this part is very important, that it is a full binary tree, and like we have been given the pre-ordered traversals of the original tree and its mirror tree. So basically, what is a mirror tree? When you invert a binary tree, it is called a mirror tree. I'll also show you what is a mirror tree and how it looks. So we have been given these like pre-ordered traversals of these two trees, and we have to construct a binary tree such that it matches both of them, right? It should be in accordance to both these pre-order and pre-mirror order, right? So this is a problem, and they also say that this is like this part that is given in the note is actually true, that it is not possible to construct a general binary tree using these two traversals that have been given to us. I'll also show an example when this is not possible, and like actually it is possible, but there will exist one or more possible answers. So that is why they say that it cannot be constructed without ambiguity, right? So let us discuss the sample test case first. So if this is the sample test case that have been given to us, first we'll discuss this particular sample test case, then we'll discuss what is a mirror tree, and then we'll see some more examples, and then after it we are going to discuss how it is not possible when the given tree is not a full binary tree, and if it is a general binary tree, why it is ambiguous to form a tree, right? So we have a couple of things in line. Now for this particular tree, this is the original tree. If I try to construct its mirror tree, it will be something like this. You see that all the nodes, so basically what is happening is, for all the nodes, the left and the right children are getting swapped. So for the node 1, its children got swapped. For the node 3 as well, the children got swapped, and it goes and keeps on going on. So you see that this matches the pre-order traversal of this particular thing, that 1 is there, then 3, then 7, like 1, then we go to 3, then we go to 7, and then we come back to 4. So it should be 6 here. This is not 4, this should be 6, right? So it is 6 now. Now we come back to 2 here, then we go to 5, and then we go back to 4, right? So this is going to be the traversals, and you must be already familiar with the pre-ordered traversal of the original tree. I just wanted to show you how is a mirror tree formed, or how is an inverted binary tree formed. That is why I showed you this. What is happening is, for each of the nodes, each of its children are getting swapped, right? So this is what we mean by a mirror tree or an inverted binary tree. So this is what we have in the beginning. Now there is one very interesting thing that you would observe if you have a tree like this, right? So this is 6 and this is 7, right? You will always observe, if I try to make an inverted binary tree of this, or a mirror binary tree, whatever you can call it, this is 7 now, this is 6, and this is going to be 5 and 4, right? So if I want to form like a binary tree from the pre-ordered traversal, what is my necessary condition? I know that 1 is the parent, right? 1 is the root node, and the left child can be 2, and its left child can be 4, right? Now if this is the pre-ordered traversal, now 5 can also be the left child of 4, right? This can be 5 as well, right? And in the if a tree is like this, then also it would be a valid pre-order traversal, or I can just extend it also. I can just write it as 3. This, let's say this is the left side, and 3 is left child is 6, and 6 is left child is 7, right? If I make a binary tree like this, and these are all left childs of each other, now this is also, this pre-order traversal that has been given to us is also a valid pre-order traversal of this particular binary tree, right? Because this is going to the left. So this is not the answer in this case, right? The answer is this one. How do we know when to stop? This is our next question, because we can always like keep attaching nodes to the left and keep on extending our binary tree, and it will still be a valid pre-order traversal that has been given to us. So we need to know a point where we can stop this traversal and we can stop going to the left. So we can know when we can stop going to the left by a very simple yet effective manner. So since we have been given a mirror tree, right, you will always observe the first node that has been like that has all the children visited, right. I'm not saying that it does not have any children, I'm saying all the children visited, because it will also occur for all the other elements other than the leaf nodes, right. The node which has all its children visited will be the last node in the mirror list. You see, in the mirror list, pre-order mirror list. So what do I mean by this? So when you can easily check whether 4 has visited all its children or not. How do we check this? If we check the mirror list, then 4 should be the last element present in the mirror list, right, like this. If it is the last element present, that means 4 has all its children visited. So in this case, it does not have any children. So obviously we don't need to visit its children. So we can just go back from 4. What we did was, we initially marked 1, we made a left child 2, then we made a left child 3, and then we realized that 4 already has all of its children visited. In this case, 4 did not have any children as well, right? So we can just cut off 4 from here. Now we go back, and the next element in the pre-order, in the main pre-order list is 5. So we visit 5. Now we check whether all the nodes of 5 has been visited or not. Yes, 5 is the last element. That means all the nodes or all the children of 5 have been visited. So I remove it, or I can just maintain some pointer, I can just decrement it, and I go back. Now my node is 2. I need to check whether all the nodes or all the nodes of 2 has been visited or not, right. So whenever I go back out from 2, I can just remove this 2, right, and then I go to 6, right. And in the original tree, I have visited till 5. So the next element in the pre-order list is 3. So attach 3 to the left of 1. Now since 3 is not equal to this last element, I can again attach one element to the left of it. So the next element is 6. So I can attach 6 to the left of it. Now 6 is equal to the last element. So what I can do is, I can decrement my pointer, or I can remove it from my array, and my pointer now is here. So the next element of 3 is 7, right. Now in this particular case, the last element is equal to this particular element, so we will not have to traverse further. So 7 is also removed, then we come to 3, 3 is also removed, and then we come back to 1, 1 is also removed, right. This is what is going on. So how is this particular mirror tree ordering helpful to us? So if we look carefully, then this particular mirror tree ordering that has been given to us like this in the second array will actually help us determine whether there are any more children of a particular node that needs to be visited or not, right. If the current node is equal to the last element in the mirror tree ordering, then that means we have already visited, either we have already visited all of its children, or it doesn't have any children at all, right. It can mean either of things, but in a more general case, we can say that we have visited all of its children, right. So if it is equal to the last element or the element marked by the pointer, then it means that we have already visited all of its children. Now we can either maintain a pointer, or we can just remove these elements from any, like if you have a vector, we can just pop back the last element, or like it's up to you. The way I implemented it during the in this problem was using maintaining a pointer, right. It's just an index variable. So this is what we'll be doing. So let us discuss some more examples. So in this case, this was a complete binary tree, but we can also have a full binary tree. So the difference is, in this complete binary tree, all of its children has exactly 2 nodes, all of the nodes. But since we have been given a full binary tree, all of its children can either have 0 or 2 nodes. So this is also very important, because once you find the left child, you already know that you also have to traverse to the right side, right. This is very important. So once I know, like this can be like this, and this, let's say the tree structure is something like this. This is 2, this is 3, this is 4, this is 5, right. So let me just write the what do we say, pre-order first. So the pre-order would be 1, 2, 3, 4 and 5. Now let me just construct a mirror of this tree. So the mirror would look something like this, 5, and then 2 will come here, and then 2 children will get swapped, so it will be 4 and 3, right, like this. So if I write the pre-order of this particular tree now, so it will be 1, 5, 2, 4 and 3, right. So now I start constructing the 3. First of all, 1 will be at the root, right. So the left child of 1 is 2. So I have implemented 2, right. So is 2 the last element in this particular list or not? It is not the last element. So I can further extend this particular 2 to 3, right, because 3 is the next element here. is this 3 the last element in this particular list or not? Yes, it is the last element. That means it will have no children further. So I can just delete this 3, or I can just decrement my pointer. So my pointer goes up to here. Now I come to 4. So obviously if I have done the left child of 2, then I'll have to do the right child of 2. So it is 4 here. Now is this particular element equal to the last element in this particular list? The mirrored pre-order list. Yes, it is the last element. So I can just remove it. That means I cannot further extend this particular 4. So I go back to 2. So I have already visited 2. So you see in this particular list has 2 functions, right? So it is also telling you that there are no further children, and it is also telling you that you have already visited all the children of the current node. So in this case you will see that you have visited the children of 2 and the last element is 2, right? So this is also indicating that there are no further children to visit. So you can just decrement this or delete this element. So you go back to 1. Now this 1 is not equal to this 5. That means there are still some more element that you need to visit. Since we have already visited the left tree, I can extend this tree to the right and I can add this element 5, right? Now in this particular case, I see 5 is equal to 5. So I can just delete this element. 1 is equal to 1. That means I have visited all the children. I can delete this element, right? So this is how the problem will be going on. So I've already discussed the main approach of this problem. Now let us just discuss some interesting things about this problem. So it's just that they say in the note that it has to be a full binary tree. That means if a node has either 0 children, it is okay, or it should have 2 children, it is okay, but it should not have any one child, right? Why is it important? I'll show you with an example. So let's say if the tree was something like this, right? So this is the original tree. If I try to make a mirror tree of it, so 1 will be here and the left and the right childs are swapped, so 2 will be here, and the left and the right childs are swapped of 2, so 3 will be here. So in this case, the pre-order traversal will be 1 and then 2 and then 3. In this case also the traversal will be 1 2 3, right? So if you want to form the original tree, it can be this tree also, it can be this tree also, because let's say this, if you took this tree as the original tree, then its mirror would be 1 2 and 3, right? So there will be 2 answers for this particular problem. One tree will be like this and the other tree will be like this, right? So obviously it is possible to form an answer, but they will have to implement a checker function to check whether the given output by you is correct or not, because there can be multiple possible answers in this particular case. That is why they mentioned that it is going to be full binary tree. So each node will have either 0 children or 2 children, right? So this is all about the problem, and I took some time in today's video. I would have uploaded it earlier because I was exploring this particular thing. I was trying to implement my problem in such a way so that it also handles this particular situation, but later I decided that let me just upload the video first and then we'll do it later. So this was all about today's problem of the day, and now let me just show you the code. The implementation is not very difficult. So what I'm doing is I'm just creating a null pointer. So this is going to be my head, and I'm initializing my post variable. So this will be the pointer which will keep track what is the last element in my pre-mirror list, right? So this is starting from size -1, and I have an index variable. So this will traverse to the pre list, right? And post is going to traverse to the pre-mirror list. Now I just call my construct function and pass my head to it. So here I receive my current element. So if index is equal to 0, that means I have to initialize my head first. So I just mark current is equal to new node pre of index, right? So this is going to be the first element. Now if if the data of the current element is not equal to pre-mirror of post, that means if the data of the current node is not equal to the last element present in the pre-mirror list, right? So what I do is I know that it is going to be a full binary tree. That is why I call the left part and I also call the right part together, right? Because it is going to have either 0 children. If it had 0 children, this part would have not executed. Now if it has at least 1 children, then I have to call both of the parts because it is a full binary tree. So I can call this function on the left. So this is the left of the current will be new node, and I'll just increment the index variable, right? So I'm just pre-incrementing it. So index will get incremented by 1 and this value will be taken from the pre list, right? So from this particular vector or the array. So once now calculated the value of the left node, I just call the construct function again on the left node. Similarly, I do the same thing for the right node as well, and I just call the construct function on the right node. So when I'm exiting the current node, I'll decrement my position. That means basically I have found a position where current data is equal to pre-mirror, and I'll just get back or delete this last element or decrement my pointer by 1. You can say any one of them, it's all the same. So in this case, I was decrementing my pointer by 1. So this is how the construct function works, and at the end you can just return the head of the tree. So this was all about today's problem of the day. Construct a full binary tree, and I hope that you guys were able to understand the solution. If you guys did, then consider dropping a like on this video. And I see a lot of people who watch these videos have not subscribed yet. So if you're one of them, consider subscribing. It's always free of cost, and you can always unsubscribe later if you don't find the videos interesting. So till the next video drops, share the channel with your friends. Keep coding. Stay safe. Bye bye.